Okay, so today I'm talking about symmetry, specifically towards graphs and equations. This is something that is not really necessary unless you're going into higher level math classes. So if this is like the only math you need to take, this is less important, but it is of interest for people who might be in art to talk about symmetry in terms of mathematics. So there's some connections there. So when we talk about symmetry in math, we can have things that have symmetry anywhere on a graph, but we're looking in math, at least, we're looking in three different specific types. And so we're usually looking for whether it is symmetric across the x-axis, which is a mirror image across a horizontal line, the x-axis, or we're looking if there's symmetry across the y-axis, which would be a mirror image across the vertical. Or we also have symmetry with respect to the origin, which actually is a reflection across the line y equals x. So it's kind of at a diagonal. And you can have graphs that have more than one type of symmetry, but these are the three types that we're usually interested in. And symmetry kind of comes up more important when you're doing anything with image processing. And if you recognize that there's symmetry in an image, you can kind of save yourself some time in how you're processing it. But you know, it's not like something that you're going to encounter daily. It's just a point that, depending on where you're going, you may end up coming across something like this and finding it useful. So specific definitions of symmetry. So there's not, it's kind of hard to put into a definition. Even the book doesn't really have a definition, so I kind of put this in my own words. If something is symmetric across the x-axis, then when you plug in a negative number for y, it will give you this, you'll get the same x value as if you have a positive version of that y value. Or if you have an equation, your equation will look identical after you do some simplifying. And it's much easier seen if you look at it in these graphs. So symmetric across the x-axis, for the same x value, you have a positive y and a negative y. They give you the same x value. So if we look at symmetry across the y-axis in the middle, if you have the same y value, you'll have a positive and a negative version of x. And so we test this, or we do this using the equation by plugging negative x into your equation and then seeing, can you simplify it and get the same y out? Then symmetry with respect to the origin, you plug in both negative x and negative y. And then once you simplify it, you see, do I get the same value, the same equation out? Basically, do those negatives cancel each other out in my equation? Once I do some math, looks the same. It's a lot easier to understand this once you kind of see what we're doing. And what we're doing with symmetry is more along the lines of what you might do as a mathematical proof, where you're basically following the rules of algebra to prove something. And you just do a lot of manipulations, and you're trying to make those manipulations look in a certain way. And then to see, can you make it look the same as what you started with, essentially. We do have symmetry with respect to functions. So you can have symmetry, things don't have to be a function to have symmetry, but if we do have functions that are symmetric, we use function notation. And so the way you're looking at that as if your f of x is the same as negative f of x for your symmetry across the x-axis. Symmetry across the y, f of x is the same as f of negative x. And then if it's symmetric with respect to the origin, a negative f of negative x is the same as f of x. The way I just think about it is if I'm testing across the x, I plug in negative y. If I'm testing across the y, I plug in negative x. So it's kind of, you do the opposites. And then testing across the origin, you plug in negatives for both. So I just try to think in terms of the x and y, you do the opposite of what you want to do. And then for origin, you plug in negatives for both values. Now, we also have definitions of functions. We can call a function even or odd, and even and odd functions have specific types of symmetry. So first, in order to be even or odd, it needs to be a function, because if it's not a function, it doesn't qualify. But then an even function is one where it's symmetric with respect to the y, so that's a mirror image across the y-axis. So an example of an even function would be like a parabola. Or an odd function with respect to the origin, and an example of an odd function is actually a cubic function. So to determine if a function is even or odd, you need to then test to see if it has these types of symmetry, and then that can determine whether it's an even or an odd function. And a function can be neither. It doesn't have to be one of these different types because it may have no symmetry at all. So I did my best to put these in directions. So when we test symmetry to see what type of symmetry it has, we don't want to plug in ordered pairs because one ordered pair may work, but another one might not. So if you try to test by plugging in ordered pairs, that's calling basically like a proof by example, and it's not a very good way to prove something because you're proving that it works for those examples, but not that it works for everything. And our goal is to prove that it works for everything. And so that's why we're going to be plugging in negative x or negative y, or plugging in both negative x and negative y, because that proves that no matter what x or y is, it will prove that it will have a certain type of symmetry or it won't. So we have to actually do some algebra manipulations here. And we can't just say, oh, we can't just do the first type of symmetry, y-axis symmetry, and then stop, because you can have multiple types of symmetry. It could be symmetric across the x, y, and the origin. So just because it has one type of symmetry doesn't mean that it doesn't have the others. So you do have to go through all three tests if you're trying to determine symmetry. So there's no shortcuts there. So basically, we're just going to go through tons of examples here to show you how you do this, basically. And I tried to choose different types of equations, solve for different variables so that you get a real good variety so you understand what you're doing here. So I'm going to just start by labeling. So we're going to be testing y-axis symmetry. And then we're testing, or I said y, I meant x-axis symmetry. Then we're going to test y-axis symmetry. And then we're going to test symmetry across the origin. So we have to test all three things to determine, and then it's either basically going to be like a yes, no, yes kind of thing. So when you are testing x-axis symmetry, you replace y with negative y. So I'm going to just do that in a different color here. So everywhere I see y, I'm just basically replacing with negative y. And I'm putting it in parentheses because sometimes you have to do some multiplication when you have these negatives. And so I'm just going to automatically put parentheses around it to determine whether, just to make it clear that's what I plugged in. So we first, for x-axis, we plug in negative y, and then you want to solve your equation for y and see if you get the same equation that you started with that I have written on the top. So in order to solve this for y, we have a negative y, we want y, so we're going to divide everything by negative 1. So that gives us y equals negative x squared minus 5. And then you ask yourself, is this equation the same as that equation? And they're not the same. So if they're not the same, that means there's no x-axis symmetry. So there's not really a lot of math work to go on. It's just you're plugging in your thing, and then you're trying to get it in the same form as the equation you have, and then you see if they match. So next is Y-axis symmetry. So to test Y-axis symmetry, you plug in negative x. So my equation has y equals, so that just stays the same. But now we're going to plug in negative x instead of x. So I have to have that in parentheses here because we're squaring. So that's negative x squared plus 5. Now we want to simplify. In this case, we're going to simplify the right side and try to get the right side to match so that we have the same equation. So when you square a negative x, so this might be hard for some people to kind of figure out what's going on here. So we can rewrite this as negative 1 x squared plus 5. Just to put it in negative there. When you're squaring, our rules of exponents say that applies to both. So we're squaring the negative 1 and we're squaring the x. So we have y equals negative 1 squared, and then x squared plus 5. And negative 1 squared is equal to 1. So this just gives us y equals x squared plus 5. And then once you've simplified that, you look, is this the same as the equation we started with? So does this match what we have up here? And the answer is yes, those match. So we did some simplifying, and now we got our equation back out. We have the same equation that we initially started with. And because those match, that means yes, there is y-axis symmetry. So if it matches, the answer is yes. If it does not, the answer is no. So then to test the origin, you want to plug in both negative y and negative x. And if you really understand how like the equations work and you've kind of seen how it takes care of the negatives, you can look at this and say immediately that this is not going to have origin symmetry. And I know this because when I plug in a negative x, it's going to cancel that out. But the negative y, we couldn't cancel out the negative y. But we're going to go through the steps anyway just to verify that so that you can see what math you would try to do to make that work. So to test the origin, you plug in both negative y and negative x. So we're doing both of these at the same time. We know negative y just stays as negative y. And because of our work for the y-axis symmetry, we know that negative x squared will give us a regular x squared because we just did that same thing on the left or in the middle here for the y-axis symmetry. So now we're at what we had with x-axis symmetry. And if I try to solve this for y by dividing everything by negative 1, I get negative x squared minus 5, and that does not match. So this is no symmetry across the origin because we didn't end up with the same equation that we started with. And the issue was that negative y, there was no way to kind of cancel out that negative. So the goal with when you're looking at testing something for symmetry, if the equation has a way of canceling out the negative that you plugged in, that is a good sign that you have symmetry. So if there's no way to kind of cancel out that negative, then that means that there's no symmetry there. Are there any questions?
Stephanie, so I mean, I understand working the math out on the three examples, but is it safe to assume that if one of these, either the X or the Y is a no, then the symmetry would be a no?
No, actually.
Okay.
There are cases where you may have no x-axis and no y-axis, but those two negatives will cancel out and you do have origin symmetry.
Awesome.
And there are times where you may have no and yes, and then something they somehow cancel out and you will have origin. Like, it really depends on the type of equation. So unfortunately, there's no easy way. We have to do the test for every single one.
Awesome.
Drop my pen. That is a good question. Okay, so here's another one, and this one is just like the one we did, but now it's solved for x instead of y. So we're basically flip-flopping the x and y, and then you'll see what this does to our symmetry. So we're going to be testing the x-axis, y-axis, and origin. And so to test the x-axis, we plug in negative y. So x equals, and then negative y squared plus 3. So this is going to be very similar to the previous problem when we were looking at the y-axis symmetry, because we had that negative in with the squared. And the basic rule is whenever you square a negative, it's going to be positive. So I showed basically every step here in the middle on how that negative x became a positive x squared. But just knowing that any even exponent with a negative, basically the negative disappears, we know that this is going to be y equals x squared plus 3. Because that square, that even exponent just cancels out that negative. And so now we have the same equation that we originally started with. And so this would be a yes, because we got the same equation. So in this case, we have x-axis symmetry. Now to test the y-axis, you plug in a negative for x. So we'd have negative x equals a y squared plus 3. And so this is very similar to the previous example when we were testing x-axis. It's just basically we've got our variables in different positions, but the work that you're doing is the same. So we want to solve this equation for x so that we can see if we get the same equation out, x equals y squared plus 3. So when you divide everything by a negative, you get negative y squared minus 3, and it's not the same. And so this is no, we don't have y-axis symmetry. And then for the origin, we're going to test both x and y. And because this situation is basically very similar to the previous one, we're going to find that this also does not have symmetry with respect to the origin. So we plug in a negative x and a negative y. So that negative x, we can't really do anything with it just yet, but when we simplify the negative y, when you square that, the negative disappears and you get regular y squared. And so now we're basically at our situation with the y-axis, where if we try to solve for x by dividing everything by a negative, we get a negative y squared minus 3, and then that is not the same thing. So we don't have any symmetry across the origin in this case. So it's very similar to the previous example, and basically what you see is that the location of the variables matter because that determined whether it was X or Y axis symmetry based off of where the variable was. Because the previous example, where it was Y equals something X squared, that had Y axis symmetry. This example, it's X equals Y squared, and this has X axis symmetry. And you can't generalize, you can't just say anything that's X equals Y squared falls this way, because that +3 does matter. That +3 makes a big difference on the types of symmetry that it has. So constants really matter. Things added on, they can make a big difference. So let's look at one here with an absolute value. So absolute values usually trip some people up, especially with variables in them. So we're going to be looking at X axis symmetry, Y axis symmetry, and then origin symmetry. So for the X axis, you plug in -y. So we're going to have -y equals negative absolute value of X minus 2. And now to test to see if we have the same equation out, that you would divide both sides by that negative, you would solve for Y. And so that gives us a positive in front of the absolute value and then a +2. And then you can see that these are not the same thing. So there's no X-axis symmetry here. Now, if we test Y-axis, you plug in a negative for X. So it's going to be Y equals negative our absolute value, negative X. Close your absolute value, minus 2. So absolute values make things positive, but we've only really done stuff with absolute values and tried to simplify them when we've had numbers. So it's when you have variables that people kind of start getting confused. So we're going to do what I did the first time when we had that negative X squared. I'm going to first write this as a negative 1X minus 2. So the way, in this case, the way that these kind of absolute values work is there is a rule. I don't know if actually it's talked about in class. I'm going to look it up. Just Google to see if it's listed anywhere. Well, I don't. It's got to be in the book. I don't have the book open right now, but oh no, my computer, my Chrome has frozen. So once my Chrome unfreezes, I'll show you the website that I just looked up. But at least I can still do my thing here. So there's a rule that if you have things multiplied inside absolute values. So like if you're having the absolute value of A times B, this is equal to the absolute value of A times the absolute value of B. Okay, the website just popped up for me. So these are some rules for absolute value. I know that our book gives this definition here, and we've used this definition. We know that it's greater than or equal to 0. I don't think that I've seen these necessarily in your textbook, but there's a rule where you can, if you have things multiplied inside the absolute value, you can separate those out. Now, this does not work for things added or subtracted, and they're not equal. Those are actually inequalities. So note that absolute value of A plus B is not the same as absolute value of A plus absolute value of B. But we're going to use this rule right here where when you multiply them, you can separate out the multiplications of the variables. or the absolute values. So I'm going to rewrite this as y equals negative. Then I have the absolute value of -1. And I'm trying to make my absolute values look really big so they don't look like ones. And then I have my absolute value of x, and then -2. So looks very confusing right now. But this will allow us to simplify, because the absolute value of -1, so I can do this part right here. I can take the absolute value of -1, and that will give me a +1. So that will simplify. So that becomes a +1. So then I have a negative, and you can put a 1 there, and then absolute value of x -2. But that 1 is not necessary. And so we actually get out the same equation that we started with. So I wanted to show this one because I wanted to show kind of how you simplify something with an absolute value of x and an absolute value of -x. When you have that absolute value, the absolute value on the x part doesn't disappear because we don't know whether x is positive or negative. So the absolute value on the x doesn't disappear, but we can take that negative and make it positive because we know that's a number, and the absolute value of the number becomes positive. So just a little kind of tricky thing here when you deal with absolute values and then you're trying to test with symmetry. But because we got the same thing out, we do have a symmetry across the y-axis here because we got the same equation out. And then to test the origin, this is going to end up in the same situation as those other ones did, where our -x is going to cancel out, basically, and kind of give us back the same thing. But the x won't, or the -y will not, because we're just going to have a -y, and we're going to end up with dividing it out, and we're going to end up with a negative sign. So just by using logic here, I can say that we're not going to have some symmetry across the origin. Now, if I had something squared with the y and something maybe squared with the x, or maybe they both had absolute values, then I would go through just to double check it. And always double check it if x and y both came out as no, because it's possible the origin is also yes. And of course, it's possible to be no and yes here and have origin yes. But I'm just kind of using my logic and an understanding, okay, if I'm plugging in a -y, we couldn't cancel that out, but we could cancel out the -x. So that's going to give us a problem. Because for origin symmetry, you need to be able to cancel out the negative for both x and y. So you could use some logic to kind of shortcut yourself here. I would recommend for you guys to go through the math just to verify it, because it's good practice. But you know, if you've done this often enough and you really understand how this all works, you can kind of look at it based off of your x and y, and you can say, okay, no, it's not going to have symmetry across the origin. Are there any questions? Okay. Here I have an equation of a circle. So this is x squared plus y squared equals 9. And if you know what circles look like, you know that there's going to be symmetry. When you have equations of a circle, it's all about where is the center. If you have a circle and the center is at the origin, then it's going to have all three types of symmetry. But if it's centered somewhere else, you cannot say that. It may have some symmetry and may not. So this is one of the reasons why you learn all these types of equations, and we want you to be able to look at an equation and understand what it looks like, and to make that connection and say, oh, this is an equation for a circle. This particular equation has a center at the origin, so I know what it's going to look like, and then you can determine, you can just see it in your head and say, okay, I'm going to have symmetry with all three of these things. But if you don't, make that connection between the equation and then understand what it looks like, you still need to go through the process of doing the math. But looking at this and you understand, okay, this is what the graph is looking like, you can understand and you can answer the question on the symmetry. But we're going to go through and do the math to show you. So x-axis symmetry, we're plugging in negative y. So my x squared plus is the same. Then instead of y squared, I'm going to have negative y squared equals 9. So I want to simplify that negative squared. So we've discussed this before, that if you square a negative y, you get a positive y out, or a positive y squared out. So that negative basically cancels out, and we're left with x squared plus y squared equals 9. So here we got the same equation. That's the equation that we have, that we were given. So there is symmetry here. Now to test y-axis symmetry, you plug in negative x instead of x. And you're going to see, because of the square, that you can kind of start seeing the pattern and be like, oh, I'm squaring a negative x. We've seen that before. Squaring negative x gives you a positive x squared. So those are going to cancel out. And we see, okay, we got the same equation. So here we also have a y-axis symmetry. So we have both here. Now, next we test origin symmetry, and that's where you're plugging in both a negative x and a negative y. And based off of what I've seen so far, I know that both of those are going to cancel out the negatives, and I'm going to end up with the same equation. But we will go through the algebra. So I'm plugging in negative x into the x squared. I can actually get my square root right there. And then I am plugging in negative y into y squared, and then equals 9. So when you square negative x, the negative cancels, so we're left with x squared. We square the negative y, that cancels, we're left with the y squared, and we got the same equation. And so this tells us that we also have symmetry across the origin. We don't usually say origin symmetry. We'll write it as symmetry across the origin. Are there any questions? Okay, here we've got absolute values of x plus absolute value of y equals 6. So we're going to do the x-axis symmetry, y-axis symmetry, and origin symmetry. Now, before I start doing anything, based off of what we've done so far, you can look at this equation and kind of get an idea of what type of symmetry it's going to have. So I want you guys to just type in the chat, just looking at the equation and based off of the examples you've seen so far, what kind of origin do you think, or origin, what kind of symmetry do you think it has? Okay, Jack, you say all three. I know we've got a few other people. Anyone else want to put some guesses out there? Nobody else is brave enough. Well, Jack, you are correct. This is going to have all three types of symmetry. And when you have things with absolute values, or you tend to have things with even exponents, like we saw with the x squared, those tend to have symmetry. And then it's just a matter of, are you able to do that on the x and the y to kind of see what is it going to be canceling out. So here, so the x-axis symmetry, you plug in a negative for y. And so our absolute value on the x stays the same. And then we're taking the absolute value of negative y instead of regular y, and then equals 6. So that absolute value of that negative cancels out that negative. We saw that in a previous example. So this simplifies to the absolute value of x plus the absolute value of y equals 6, because the absolute value removes the negative. Now, it doesn't remove the absolute value around the y, because we don't know whether y is positive or negative, but we can for sure remove the negative because it makes things positive. And so that gives us our same equation. And so we have x-axis symmetry. And you'll see that for x or for y-axis symmetry, you plug in a negative x, and you're going to have the same thing because it's, you know, there's patterns here. You're going to see that that negative that we plug in, that negative inside the absolute value is going to cancel out. And that will just give us the absolute value of x plus absolute value of y equals 6. And now again, we have the same equation out. And so we also have y-axis symmetry. And then because we know we can cancel out the negative with the x, we know we cancel out the negative with the y, testing the origin where you're doing both, you'll see that we will also have symmetry across the origin. So that negative sign cancels out on the x, and we're just left with the absolute value of x. The negative cancels out with the y. So we have absolute value of y, and we get the same equation. So once again, we do have symmetry across the origin here. Okay, now I'm getting into ones where we're going to be plugging into our negative into more than one place. Like so far, we've only had one variable to plug them in. Here, when we plug in like a negative x, I have to do it in multiple places. And so this is where, you know, you've kind of seen the pattern so far with all the examples we've had. This is where you might start getting interesting combinations where you may have no x or only y, and then you also have origin, or you may have no origin, or, you know, it starts to do some interesting things. And usually situations like this, I don't like to guess as much on the type of symmetry I'm going to have. I mean, I can look at it, I can kind of mentally, but you're more prone to making mistakes. So I usually don't try to guess when I have an equation like this where I have multiple places I have to plug things in, because there's more moving parts. So to test x-axis symmetry, we're plugging in a negative y. So I only have y in one place here, so that's nice and easy. And then there's not a y on the right side, so the right side stays the same. So to test to see if we have the same equation, I want to divide everything by a -1. And I'm just going to show that here because it's a little, you know, we want to make sure we're not making any mistakes. And with the absolute value particularly, when you're dividing the absolute value by a -1, that negative goes in front. Because the absolute value is positive, you're dividing it by a negative, so you're going to get a negative. So you put a negative in front of there. And then we end up with a minus 2x plus 7. So now we don't have the same equation. Like, this is not the same thing that we started with. And so we don't have x-axis symmetry. So now let's take a look at y-axis where you plug in a negative x. So I've got, make sure I got my right color, y equals, and then I'm going to plug in a negative x into my absolute value. Plus 2, and then we're multiplying that by negative x because we're replacing x with negative x. And then minus 7. So we've got multiple things to simplify here. We've got the absolute value of negative x. So we've seen that before. That negative cancels, and we're left with just the absolute value of x. Then we've got 2 times negative x, so that's negative 2x, and then minus 7. And now we look to see, do we have the same thing? We almost have the same thing, except for the sign in front of the 2x. Our original equation had a plus. This has a minus, so it's not exactly the same. And so we do not have y-axis symmetry. So it's close, it's almost the same, but it's not because of that one minus sign there. So now let's test the origin. I'm going to move this lower so I don't run into my other stuff. So to test symmetry across the origin, we want to plug in a negative for both. So we have a negative y equals absolute value of negative x plus 2 times negative x, and then minus 7. So I'm going to just start by simplifying the right side. So I still have negative y on the left. The absolute value of negative x is equal to the absolute value of x. Then I have minus 2x. Then I have minus 7. So to test to see if I get the same thing, let's divide everything by negative 1. So I'm going to divide everything by negative 1 so that I can solve for y. So I get y equals, now we've done this work before. We know that negative is going to go in front of the absolute value. Then we have a negative 2x divided by negative 1. That's a positive 2x. And then we get a positive 7. And so now here we look and we say, do we have the same thing? Almost, except that we have a minus in front of the absolute value that we don't want. And now we have the wrong sign in front of the 7 that we don't want. So it's kind of similar, but it's not the same thing. And so here we don't have any symmetry across the origin either. So in this case, there's no symmetry at all. This would be one of the cases where you would say it's none of these, because it failed all 3 tests. And looking at it, you may not have necessarily been able to tell that. Like, you might have said, okay, I can look at the x. I know that plugging in negative x is going to cause a problem, but maybe if I plug in a negative x and a negative y, they'll cancel out. But they don't. So, you know, it's harder to kind of look at these and kind of do it in your head when you have multiple things you're plugging in. Are there any questions? Okay, so this is my last example here. And so this is a quadratic equation. We have y equals x squared plus 5x minus 12. So when you're looking at this, you want to think of this in terms of being very similar to the one we just did. We've got an x squared instead of like an absolute value of x, but those kind of operate the same way when you're testing symmetry. And so based off of our experience on the previous example, that we had problems with the signs being different, with the 2x, and then we have this -7, just generalizing based off of patterns we've seen and how this is similar, because the absolute value of a negative x operates sort of the same as the x squared, or a negative x squared, where the negatives cancel. We still have something with an x added on. We still have a number subtracted. So these are very similar in type. And so we should expect the type of origin to be similar, being that there is no symmetry here. But we should go and mathematically test that just to be safe. But one thing I want you guys to kind of get out of this is trying to find similarities between equations and pieces of equations based off of what you're trying to do. Normally, we would not say an absolute value is similar to an x squared, but in terms of we're plugging in negatives and they cancel out, they are similar. And so you can use that to kind of help you see patterns here. So it's kind of trying to find similarities even if they don't look exactly the same. So X axis symmetry, we're going to plug in a negative y. And hopefully we've done this enough that you kind of see exactly what we're going to do. We're going to divide everything by a negative, and it flips all the signs. And then because we flipped all the signs by dividing by a negative, we no longer have the same equation. So there's no symmetry here. Now, y-axis symmetry, we plug in a negative x squared. So first I got my y equals, then negative x squared plus 5 times negative x, and then minus 12. So we've done a lot of this work before. You square a negative x, you end up with an x squared. 5 times negative x will give us a negative 5x, and then a minus 12. And then we are almost the same, but not quite, because of that negative 5x. And so this is very similar to the previous example, where not everything canceled out. And so this means that it is not, there's no symmetry across the y-axis. So following that, I'll move this down again. Then when we're testing symmetry across the origin, and you'll see, oh, okay, this is going to be very similar to the example we had with the absolute value. We're going to try to get rid of the negative in front of the y, but it's going to cause us some problems with the signs in front of all the x stuff. So to test the origin, we plug in negative y, and we plug in negative x. So I'm going to simplify the right side first, which we've done that before. So you're basically just reusing the work that you had to test the y-axis symmetry in this case. And then we want to divide everything by a negative so that we can see whether we can get a positive y. So I'm going to just divide each of these by a negative. So we got y equals negative x squared plus 5x plus 12. And then in this case, only the 5x part has the correct sign. And so this has no symmetry across the origin. That's not exactly the same. Are there any questions? Okay. So there are other combinations of these things that you can have, like if you have x and y on both sides, like an x and a y on the left, x and the y on the right, whether you have things with squared, not squared, cubed. Like there's lots of other different combinations of whether things are symmetric. But you'll start to see patterns, and hopefully you've seen sort of the tricks on how to figure some of these out, so you'll be able to apply those tricks. So if you plug in a negative something and you have an exponent, if it's something other than a square like we've done, like if you have an x cubed maybe, if I can get my screen to, oh, I didn't want that slide. I wanted this slide, there we go. So if it had like a x cubed, you can put the -1 in front of the x. Instead of a negative x cubed, you put a -1x, then cube it. And you can use that trick to help you simplify it. So like a -1 to the third power is negative. It wouldn't cancel out in that case. You'll frequently be using the trick where you divide both sides by a negative in order to try to cancel out negatives. Tricks you'll often use with absolute values are the same thing that I did here, where you can get that absolute value. If there's a negative inside, it can pull out. So you'll kind of start doing the same tricks over and over again with these types of problems. So like I said at the beginning, you don't really deal with symmetry unless you're doing stuff with image processing or images. But one thing it does kind of help teach you is just reinforcing the rules of algebra and being able to manipulate stuff. And also kind of gets you thinking, well, I want it to look a certain way. What do I do to get it to look like that? Can I make it look the way that I want? Like in this case, you're saying, I want to make my equation look like the original. What can I do to try to make that happen? So it does kind of get some critical thinking going on there to try to, think about different ways that you can simplify equations and what you can do to them. So there's some, some benefits, even if you're not going to be sitting around at your job testing whether things are symmetric. Most people will not be. So hopefully this was helpful for you guys. I mentioned even and odd functions, but when you're testing something to see if it's an even or odd function, you're basically, first you need to determine if it's a function. If it's in function notation, like it says f of x, that part's automatically true. And then when you're testing them, you're testing the different types of symmetry. An even is symmetric across the y-axis, and an odd is symmetric across the origin. So you're only testing 2 of those types. And what you can do is, instead of using f of x, you can just use y, because f of x is equal to y in a function. And then you can basically do the same thing you did here. So when you're looking for even or odd functions, just replace f of x with y and then do the test for symmetry, and that will help you determine whether it's even or odd. So it's not really anything new from what we've already done here. It's just different terminology, just a little twist on it with the f of x. So, are there any questions? All right. Well, thank you guys for attending. I really appreciate this. I'm going to make sure to email this video out probably tomorrow afternoon for the recording when I have my office hours. So you'll get an email then with the recording and all the documents and stuff. So thank you guys. I hope you enjoy the rest of your Saturday. And I will talk to you guys at the next one.
Thanks, Stephanie. Have a good night.
You're welcome. You guys have a great day. Bye.